Alright, so this says let rho sub m represent the volume mass density of this plate pictured below. It's a parabolic shaped plate, so it has a nice mathematical function, but it's not something where there's like a known geometry formula like pi r squared, or most people don't know what the formula would be for this partial parabola here. So we're going to integrate to find the mass of it is the idea. So it says that for steel, this is a steel plate, the density is 8.05 grams per centimeter cubed, and then sigma sub m can stand for the plate's area mass density. And so these are things that are used in calc and physics all the time. One of them being a three-dimensional type of idea, the other being just two-dimensional, right? And it says it's with respect to the xy plane. So basically the idea being that if you know you have a certain patch of area there, A, then you can find the mass of that patch by doing mass equals sigma m times A. Because what happens is the sigma m has units of grams per centimeter squared, and then you multiply by centimeters squared, so you end up getting grams. But when you do it for a volume, then you have a three-dimensional thing, which would be like a cube of area. And so now you would know the volume of that little piece. And so when you want to find the mass, what you do is you multiply by rho, the volume mass density. And so volume mass density has units of grams per centimeter cubed. So you multiply by centimeters cubed and you get grams, is the idea. So let's see if we can find the area mass density for this particular shape. Alright, so area mass density and volume mass density have a relationship. The relationship would be that the area mass density is the volume mass density times T, which is the thickness of the object. If we take our volume mass density and then multiply by the thickness of this plate, which is a 0.06 meter thickness. We want to correct for the units, so let's do 100 centimeters per meter. Cube that conversion factor. See what that comes out to. Yeah, 483,000 grams per meter squared. Alright, or 483 kilograms per meter squared. Alright, now that we have that, let's see if we can do some integration of the area of this parabolic shape. Alright, so we'll integrate to find the area. We'll go from x equals -2 to x equals 2. And we want to put our function in the integrand, so 8 minus 2x squared. Typically leave the units off in these integrals, just for simplicity's sake. You'll get 8x minus 2/3 x cubed. It's a definite integral, so we'll go from -2 to 2. We'll plug that in. Yeah, so let's show that. 8 times 2 minus 2/3 times 2 cubed minus 8 times -2 minus 2/3 negative 2 cubed. Looks like 21.3. And that's going to be meters squared. All right. Now at that point, we have a couple of options for finding the mass. We could simply go off of this here, this formula, since we know the area and we also calculated the sigma there. We could just use that. And just to be clear, what I did in the integration, I was of course breaking up the thing into an integration like this, where each little piece has a dx. I was just finding all the area of those little strips. That's what this represents, the area of the surface of it. All right, so I'll try that formula. M equals sigma times A. So 483,000 grams per meter squared times 21.3 meters squared makes pretty big mass. 10,304,000 grams, or in other words, 10,304 kilograms. Now the other option for this would have been to take your area and find the volume of the thing. So what's the volume of the plate? That would be found by V equals area times thickness. Alright, so your volume of your plate would be 21.3 meters squared times the thickness of 0.06 meters. So our volume would be 1.278 meters cubed. And at that point, you could go on to find the mass in a little bit different way. You would use the volume mass density, though. Let's see if we get the same answer either way. So the volume mass density was given originally. They said it was 8.05 grams per centimeter cubed. So it looks like we would get that. We have to do a conversion though. 100 centimeters per meter. Cube that factor. And yeah, it's basically coming out the same. Slight difference due to my rounding. So let me just keep a couple extra sig figs in there. Alright, so that basically takes this to 1.28 meters cubed if you keep more sig figs in. Alright, 8.05 times 1.28 times 100 to the third comes out same. One last question for this one is, what if we wanted the plate to accelerate with an acceleration of 3g? 3 times the acceleration of gravity. What magnitude of force would have to be applied to this plate? Alright, so for that, we're going to want to use Newton's second law, that the net force applied to the plate will have to equal its mass times acceleration. But we want to let the acceleration equal 3 times g. So, in other words, 3 times 9.8. And I'm going to give it different units. I'm going to give it the units of newtons per kilogram this time. Alright, so newtons per kilogram is just equivalent to meters per second squared. And so that would be an acceleration of they're looking for 29.4 meters per second squared. Alright, so let's plug in. In this case, it's not a vector, so I don't have to, use any vector notation. These can just be the scalar versions of the variables. Our mass that we found was 10,304 kilograms. And we want 29.4 meters per second squared. And we can also write that as 29.4 newtons per kilogram. And you can see why, right? Because what's going to happen is kilograms could cancel. And it'll give us our answer in newtons. Looks like we need a net force of 302,900. So basically 303,000 newtons. That's a lot.